Now the vector function. So if each value of a scalar variable t there correspond a value of the vector r, then that vector r is called a vector function. Here that r vector, we write the r is a function of t and that t is in a scalar quantity and the r of t, that is r, is a vector. Sometimes we write f of t in the form of function. So in 3D plane, or we can say in three-dimensional, every vector can uniquely express as a linear combination of three fixed non-coplanar vectors. So f of t, we write f1 t I, f2 t j, f3 t k. Here ijk, that ijk denotes the unit vector along the x-axis, y-axis and z-axis, and that f1, f2, f3, these are called the component of that vector ft along the coordinate axis. If we say that is in x, y, z, so somewhere the vector f vector of t, so the corresponding the ijk is what, is a unit vector, and that f1, f2, f3 is a component of the vector f along that these axes. Now the derivative of a vector function with respect to a scalar. So suppose we have a vector r, or we say of ft, be the vector function of a scalar variable. Here the scalar variable is what, t, and suppose del t be the small increment in t and del r the corresponding change in r. So suppose that is in vector r and this is a p, this is o, this is q and this is o. So a small change in p to q. So here the vector is what, r plus del r is equal to f t plus del t. There is a small increment in t. So in that case, if we find the pq is equal to, we write pq, the vector pq is what, oq minus op. So we get that vector del r. And if we write r plus del r, so it means that is vector f t plus del t. So the small change in the, you can say, a scalar variable, so a change in a vector, so that del r we can write del r is equal to f t plus del t minus r vector, or the r vector is what, ft. Now if we divide by that del r vector with by dt and take a limit del t tends to 0, so we can write f t plus del t minus ft upon del t. If that is exists, so we can say this is what, this is a derivative. So we can say dr by dt, vector dr by dt is a derivative of r with respect to t in the direction of a tangent at a point p, means a tangent at this point representing the derivative of that vector r. Now the general rule of the differentiation. So if we take a vector a, b, c are the vector functions of a scalar value t, and phi is another scalar function of t. So the derivative, if we have given the addition or the subtraction of two vectors and we have to operate a derivative over there, so we just that operate that derivative separately on the vectors. So we write derivative of a with respect to t plus minus derivative of b vector with respect to t. Now the second property, if we have given the dot product of two vectors and we have to differentiate, we operate the derivative on that. So we follow the product rule of the differentiation, that is the first vector same dot the derivative of the vector b plus the derivative of vector a dot b vector. And if we have given the cross product of two vectors a and b vector functions and we have to take the derivative over, so we write the first vector cross product the derivative of second vector with respect to t plus the derivative of the first vector, that is a, with respect to t, cross product into back vector b. You just follow the same order as we have given. Now the third one, if we have the product of a vector b into a scalar function phi. Here phi is a scalar function and b is a vector function. So if you want to apply the derivative on that, so again we have to follow the product rule. The phi is same, the derivative of b plus the derivative of phi function into dot b. And similarly, if we have given the cross product of three vectors a cross b cross c, and we have to operate the derivative, so we just follow the derivative of the first cross product of b cross c plus a vector cross derivative of b vector cross c, and a cross c cross derivative of third vector, that is c, with respect to t. The next point, if suppose we say a vector is said to be constant if both its magnitude and direction are fixed. So in that case, derivative of that vector we get 0. And the last point, if we say r be the vector function of a scalar variable t, that is we say r vector is xi plus yj plus zk, where x is equal to f1t, y is equal to f2t, and z is equal to f3t, then the derivative of that r, we just differentiate the f1 plus f2 dash f2 dash plus f3 dash, so we get our vector quantity. So the scalar and the vector point function. So a variable quantity whose value at any point in the region of space depend upon the position of the point and is called a point function. So there are two type of point functions. The first one, the scalar point function. So scalar point function is what? If the R be the region, suppose, of a space at each point of which there is correspond a unique scalar. So that is, we say phi is a function of x, y, z. So the example of the scalar point function, suppose we say the temperature distribution in the heated body is what? Is an scalar point function. Density of any body or substance is again a scalar point function. Or we say the distribution of atmospheric pressure is also a scalar point function. Now the vector point function. So again we say if R be the region of the space at each point of which a vector, a unique vector v, is given, then that v vector is called vector point function, and that r on the region r, in that case r is called vector field. So the examples are the velocity of a moving fluid, or we can say a gravitational force. These are the vector point functions. The example, a particle move along the curve x is equal to t cube plus 1, y equal to t square, z equal to t 2t plus 5, where t is the time, and find the component of its velocity and acceleration at the time t equal to 1 in the direction 2i plus 3j plus 6k. So first we write the vector function, that is xi plus yj plus zk. So we have x t cube plus 1 I t square j and 2t plus 5k, that is r vectors. Now we have to find the velocity. First we find the velocity. So the velocity is what? We take the derivative of r with respect to t. So we get 3 t square I 2 t j and 2k. Now we have to find the velocity at t equal to 1. So at time t equal to 1, so dr by dt, we have 3i plus 2j plus 2k. On the place of t, we just substitute t equal to 1. So that is in velocity. Now we have to find the velocity at time t equal to 1 in the direction, that direction. So the given direction says, we say vector t is 2i plus 3j plus 6k. So we just find the unit vector of that direction. So we get the vector and the magnitude of that vector. So we get 2i plus 3j plus 6k, and we get root the square of 2 4, the square of 3 9, the square of 6 36. So now we get the unit vector d is what? 1 by 7 2i plus 3j and 6k. Now velocity, the component of velocity in the direction d is what? Is dr by dt, the velocity, into in the direction d. So we write the velocity is what? 3i plus 2j plus 2k dot 1 by 7 2i plus 3j plus 6k. Now we take the dot product and we get 1 by 7 3 2 dot 3 into 2 we get 6, 2 into 3 we get 6, and 2 into 6 we get 12. So we get 24 by 7. So that is a component of velocity. Now similarly we can easily find the acceleration. So acceleration was d2r dt2. That is, we take the derivative one more time of that. So what we get, that is dr by dt. So the derivative of 3t square I 2tj plus 2k. So here we get 6ti plus 2j, and at t equal to 1 we get acceleration at t equal to 1 we get d2r upon d2 vector, we get 6i plus 2j. Now again we have to find the acceleration in that direction. So we just take a dot product of that with this. So acceleration in the given direction d is what? Is d2r upon dt2 into the unit vector d. So here we get 6i plus 2j and 1 by 7 2i plus 3j plus 2k. So we get 6 into 2, that is 12, and plus 6 18 by 7. So in that way we can find the solution and the velocity component of the velocity in that direction. So in that example, at any point of the curve x equal to 3 cos t, y equal to 3 sin t, and z equal to 4t, we have to find the tangent vector or unit tangent vector. So here first we write the curve, that is the vector function r, that is xi plus yj plus zk. Now we have 3 cos ti, 3 sin tj and plus 4tk. That is the vector function. Now we have to find the tangent vector. So we take the derivative dr derivative with respect to t of that function. This is the tangent vector. So we take the derivative. So what's the derivative of that? We take the derivative of 3 cos t. So the derivative we get minus 3 sin ti, derivative sine cos. So we get 3 cos t j and plus the derivative 4t, we get 4k. Now this is a tangent vector, and the second part we have to find the unit tangent vector. So we take the unit tangent vector. Suppose we just take this is the vector unit tangent vector. We take the unit tangent vector is what? Dr by dt. We take the unit tangent. So we write the vector minus 3 sin t I plus 3 cos t j plus 4k and take the magnitude of that, that is minus 3 sin t, square of minus 3 sin t, we get 9 sin square t plus the square of 3 cos 9 cos square t and the square of 4, that is 16. So here we get sin square plus cos square, we get 1, and 9 plus 16 we get 25, so we get 5, and this is the I cos tj and 4k. So this is what? This is the unit tangent vector. We just take the unit tangent unit vector of that tangent.